Well, hi there, boys and girls. Today we're going to get some notation out of the way, and we're going to learn about higher order derivatives. And so we already know that if I plan on taking a derivative, I have this notation, and you can think about this as a verb. We call that differentiate. And if I differentiate some y equals, I'm going to get a derivative. And you can think about that as a noun. This is the derivative. This is a verb. I'm getting ready to differentiate some y equals. We also have some other notation for this. We say that dy dx, make sure that's a y, don't want to get sloppy with that, this also equals f prime of x. There's another notation for that, and sometimes we can just call this y prime. dy dx is y prime or f prime of x. Now if you do the derivative again, in other words, if you ddx, dy dx, you take the derivative again. Leibniz had some weird notation. He thought about this as a fraction, and he called this d squared y. You can see how he got the d squared over dx squared. And he didn't want to put brackets around the dx, but that was his notation that he used. This stands for the second derivative. So we could call this f double prime of x, or we can also call this y double prime. Now there's also some obscure notation that you will not see very often, and that looks like this. Second derivative of x with a capital D, d squared of x. But that doesn't, you don't see that notation very often. So this would be the second derivative. This just means you take the derivative again. So I guess the third derivative should be pretty easy to follow this line of reasoning or this pattern. The third derivative would be d cubed y over dx cubed, which is the same thing as f triple prime of x, which is the same thing as y triple prime. Now, sometimes if you take the derivative repeatedly, sometimes in this notation right here, we call this the nth derivative of x. They don't do like n tick marks. So this would be equal to the nth derivative, like that. Okay, so let's go take a look at some examples. So here I want the fifth derivative of x to the fifth. So that means we're going to take the derivative 5 times. So let's just get after this. Here's the first derivative, 5x to the fourth. Then the second derivative, 20x cubed. This is like the first, this is the second. Then the third derivative, 60x squared. And then the fourth derivative, 120x. And then the fifth derivative, 120. Now I want you to notice what happens right here. This ends up being 5 factorial, which is 5 times 4 times 3 times 2 times 1. Now why did that end up being 5 factorial? We brought the 5 down and left it there. Then we subtracted 1 off that exponent and it was a 4. Then we brought the 4 down and it made it a 20. Then we brought the 3 down, the 2 down, and the 1 down. So just as a shortcut, that ended up being 5 factorial, and which was 120. Now why is there not an x in my answer? Well, I ran out of x's. If I would have done one more derivative, I would have taken the derivative of 120 and I would have gotten 0. Let's go look at another example. Let's find the 9th derivative of this big long thingy here. Well, I'm going to do the first couple and then we're going to look for a pattern. The first derivative would be 16x to the 7th minus 105x to the 6th plus 20x to the 4th plus 92x cubed minus 14x. That's f prime. Now f double prime would be whatever 7 times 16 is. That's 70 plus 42. What is that? 112 x to the 6, blah blah blah. And then I'm looking for a pattern now. Finally have a minus 14. And then f triple prime with the minus 14 would go to 0. And so what we're going to do is we're going to think about this. If I were to take the derivative 8 times, I would run out of all of these terms because they would eventually go to 0 because I'm taking a derivative that's 1 more than the power of x. Now let's back up just a little bit and make sure you understand that. If I have an x squared and I take 1, 2, 3 derivatives, So if I find the d cubed y of dx cubed, that would be 2x, then 2, then the derivative of 2 is 0. So if I take one more derivative than I have a power of x, it eventually is going to go to 0. And this term here, if I take 9 derivatives, I only have 8 x's to use. If I take 9 derivatives, that's also going to go to 0. So I'm not going to take the derivative 9 times. It's going to take me too long. You can go ahead and try it, but you're going to see that the derivative works out to be 0 because we're out of x's. Okay, now here I'm going to use that pattern. I'm going to do the fifth derivative of f of x without actually calculating 5 derivatives. If we do the derivative 5 times, I'm going to have 5 factorial in front, because I'm going to bring the 5 down, then the 4, then the 3, then the 2, then the 1. And then, on top of that, because of the chain rule, I'm going to have the 2 is going to be in there 5 times, because each time I'm going to take the derivative, I'm going to have to use the chain rule. Let me show you again what I'm talking about. Just the first derivative would be 5 times 2x plus 3 to the 4th, but then times 2. Then the second derivative would be, the 4 is going to come down, so it's 5 times 4 times 2x plus 3, and then times 2, which is, that times 2 is already there, but then times 2 again because of the chain rule. So I'm going to have 5 factorial after 5 derivatives, and then I'm going to have 2 to the 5th because I'm going to use the chain rule 5 times. Now, if I do the derivative 5 times, I am going to be out of x's. So this is what I'm going to have, 5 factorial times 2 to the 5th. And so that's going to be 120 times 32. And so that is why I'm pretty sure that's going to be B, but I guess we should just make sure. 0, 4, 2, 0, 0, 6, 3. Yeah, it's 3840. Now, why does this not matter? Well, that doesn't matter because I'm out of x's. If you take the derivative 5 times on an x to the 5th, you are no longer going to have an x. That last derivative will be multiplied times the derivative of 2x plus 3, which is just 2. You can go ahead and continue and do this if you want. The third derivative would be 5 times 4 times 3 times 2x plus 3, and then we've got 3 applications of the chain rule here. Oh, what am I missing here? Oh, I missed it here too. That would have been a cubed and then the squared. I hope you're still watching because I should have had a 3 there and then a 2 here. And then the fourth derivative of x would have been 5 times 4 times 3 times 2 times 2x plus 3 to the first. I'm almost out of x's, and then I've got 2 to the 4th. And then my fifth derivative is going to be 5 factorial, then the derivative of this 2x plus 3 is just 2, and I've got no more x's left, and that's why it worked out to be what it did. Okay, let's take a look at an example of implicit differentiation with y double prime. This gets a little tricky. So first of all, we are going to ddx, or take the derivative of x squared equals y to the negative 3. So let's go ahead and do that, because to get to the second derivative, we have to find the first one. All right, so this is going to be 2x equals negative 3 y to the negative 4, and then we have to multiply this times the derivative of y, times dy dx. So there's the first derivative. And if you want to, we can go ahead and solve this for dy dx. Equals, so we're going to get negative 2x over 3 y to the negative 4, which means I could actually take this y up here as y to the 4th. Okay, so that is dy dx. Now let's take the derivative again. So the second derivative, or y double prime, is going to equal, now that negative 2/3 is just going to sit there, and then I'm going to do the product rule. Product rule is the first times the derivative of the second, so that's 4y cubed times dy dx, and then plus the second times the derivative of the first. Now, you always want to have your second derivative in terms of x's and y's. We have our second derivative, but I've got a dy dx here. Well, what can I do? I can substitute this value right here in for dy dx. So let's go take a look at what that is. So I'm going to have negative 2/3 times 4xy cubed. And then here I've got negative 2xy to the 4th over 3. And then plus y to the 4th. So let's see if we can't simplify this a little bit. So I've got negative 2 times 4 times negative 2, that is 16. I've got an x and an x, and that's going to be an x squared. See if I can keep this right here. Then I've got a y cubed and a y to the 4th, so that's a y to the 7th. And what do I have on the bottom? Well, down here I've got a 3 times a 3, and so that's a 9. So let's see if I've done this correctly. That's just that first term. Okay, now my next term, I'm going to have minus 2y to the 4th over 3. Alright, sorry I had to pause as someone came to the door. Okay, so if we brought these, it looks like it might be e, but we don't have the correct second term, or this denominator is not the same. If you made common denominators with our second term here and called this 6 over 9, that's why this would come together 6/9. That's still 2/3 as this correct answer of B. Okay, so that's it for higher order derivatives, and I will see you guys tomorrow.